Good day, everyone. My name is Francisca Benitez, and today I'm in name of the Latinx Chem committee organizing committee. We're doing our second webinar. This time we have Professor Elisa Souza Orth from Universidade Federal do Paraná in Brazil. Let me give you a little bio about Elisa. Elisa is a professor at the Universidade Federal do Paraná in Brazil. She is the leader of the research group of catalysis and kinetics at the same institution. Her research is focused on organophosphates chemistry, neutralization and detection processes of agrochemicals and chemical warfare simulants, forensic science, chemical security, disaster mitigation, catalysis, functionalization of biopolymers, nanomaterials, and renewable resources, and also green chemistry. So basically, you research about everything. She's also She's also an affiliate member of the Brazilian Academy of Science and received over 30 prizes, highlighting the Brazilian women in chemistry and related sciences. In 2018, given by the ACS, Fosagro, UNESCO UPAC Green Chemistry for Life. In 2018, the International Rising Talents in 2016, and for Women in Science in 2015. She is a member of the Scientific Advisory Board of the Organization for the Prohibition of Chemical Weapons, and she's also engaged in gender equality and scientific dissemination activities. And right now, you are the secretary of the Sociedade Brasileira de Química, which also happens to be a committee this year of only women, from president, secretary, vice president, treasurer, which is very nice. So without further saying, here's Elisa with her talk about what she's doing. And Elisa, now you can.
Thank you very much for this kind introduction. Of course, I don't do everything. It's just a little bit of what I'm doing that I'm interested in. I am very happy to be here with this invitation to present all of my work to you. And I will also comment a little bit of the Brazilian Chemical Society, because it's something that I'm actually very proud to be part of now. And we're also related with Latinx Chem and sponsoring some prizes. So I will just comment something briefly. But let me just, first of all, share my slides and just check if you're... do you see my presentation?
Yes.
Okay, thank you. So thank you again for this very kind invitation. I'm very happy to participate as a speaker. I have been participating in this event since the first edition. I think it's a really important, strong event. And I think that the idea of us connecting, of the chemists, of the scientists from Latin America organizing themselves, it's something very important for us to do. And I really am happy to be part of this. So today I'm going to talk a little bit about how we want to tackle toxic organophosphates using different kinds of approaches, trying some green approaches, trying catalysis, and some other issues that I will present you right now. But when I talk about this, first of all, I like to say a little bit, are we safe? We ask ourselves this stuff because we see all these kinds of news, which are a problem not only in Brazil, but worldwide. And you can see here, for example, we have the use of toxic chemicals, which are the focus of my research, being used, for example, as pesticides or chemicals worldwide. And for example, in Brazil, we have a lot of concern with this because we are one of the largest producers of food. So, of course, we are one of the largest users, consumers of agrochemicals. And because of that, we need to be sure that we're using the right amount, that we are safe in the amount that we are using. But also because of that, we have a lot of illegal trade, we have a lot of illegal apprehensions, and we need to be sure how to guarantee their safe handling, how to guarantee their disposal afterwards, and how to also confirm that's something that's toxic, for example. And related to this, we had a lot of news related to, for example, intoxication, for example, in schools, the people who apply, the people who are eating the food. So all of this concerns are really related to the chemical security of these compounds. And what's interesting or not is because the same kind of molecules that are used as agrochemicals, one specific class, which is very toxic, is also used as chemical weapons. And this is also a worldwide concern, not only in regions, for example, that have conflicts. And I know we know that in regions that we have conflicts, we have this concern, but there's a concern also because they have been using these chemical weapons, not only in these places, but in places, for example, in Salisbury, places that are not in conflict, and they have been used as, for example, in attempt of assassination, because these molecules are very, very toxic. So we have been seeing this kind of news, and we need to be, for example, this happened in the Malaysian airport, for example, this assassination. So how do we protect the people who are next? How do we respond fastly to this kind of things? And also, closely related to that, there's what we call the chemical disasters. For example, this one that happened, let me just show the video, where we had, for example, this explosion in a port, which has to do with a very toxic chemical, which is also can be used as agrochemical and can be used as a chemical weapon, and is an important supplement for the industry, chemical industry. So we need to be able to know how to handle this kind of chemical disasters, right? Not only first we have to confirm what's happening, because we need to know if, for example, we can use water. In this case, you shouldn't use water, for example. But in some cases, we need to know how to quickly respond to a chemical emergency. That's what I call it. So just continue and just put my pointer. So overall, as I mentioned, so this class of molecules that we're interested are usually these agrochemicals and chemical warfares, which are these compounds that have this kind of high toxicity. And we want to tackle not only to alert, for example, attack or misuse or some kind of disaster, but also to be able to tackle undesired stockpiles, because it's very common to have stockpiles left, for example, or we have stockpiles of illegal apprehensions, and we need to know what to do with that. So one specific class of molecules that we are actually interested in is this kind, which are called organophosphates, and they have this generic representation here. And so we are interested in this kind of molecules because they're the most toxic class of agrochemicals, you can say, and which are also have a similar structure to many chemical warfares. And if you see this reaction here, you can see that if we have this, first of all, this organophosphate, which is very toxic and is known to be very stable. And if you do this simple modification, for example, if you substitute this group here for this one, I can guarantee you that in most cases, we can have in the product a very less toxic product or even non-toxic product. So we call this reaction here a neutralization reaction. But as I mentioned here before, this molecule is very stable. So this reaction is very slow. It's not favorable to happen. And the group that I work and that I lead actually is concerned in developing catalysts that can promote this reaction. So catalysts have the ability to accelerate the process, to turn it faster. So what we do is we develop different kind of catalysts, where we call catalysts on demand or by design, which are specific for this kind of reaction and can help us eliminate this kind of toxic compounds. And also we can benefit from them also to monitor the presence, because we can monitor their presence following this reaction. And I will show you some example in the following. But before I present these the results, I always like to present, first of all, my group. So the group that I lead is the group of catalysis and kinetics, and it's located in Curitiba, the city in the south of Brazil, right here. It's the oldest university in Brazil, and I invite you all to visit our medias to see a little bit more of what we have been doing. And also, I would like, first of all, to acknowledge the students which are responsible for all the exciting results I'm going to bring to you. Today, we are in 15 students. This is the most recent picture I have, and I'm very, very proud of them. I think that all of them, or I think most of them, are participating in this event and have participated in all the past events. So we are very much engaged also in this event. And I also like to acknowledge the collaborators, which are very important also for the results I will be presenting. But before I present the results, as I mentioned before, I just want to mention just quickly about the Brazilian Chemical Society, the Sociedade Brasileira de Química, which is, since we're talking about our Latin American community, I think this is a very important society because it's one of the largest scientific societies in Latin America. It has nearly 2,500 members, but we have already reached 4,000 members, and we are with efforts to increase this kind of number. And we're very proud because, first of all, we are sponsoring this event, Latinx, so we have some prizes that we are giving out. And also, it's the first directory board in which we have the president, which is here, Musimiri, and me, which are the president and general secretary. You also have other women's here, vice president. We have the vice deputy treasurer also. So you can see we have a lot of women, but it's the first time we have a woman as president and general secretary leading this important society. And it's a very important society in Brazil and also worldwide. For example, we have Publi SPQ, which is responsible for editing 4 important journals that we have, which have a lot of international prospect. For example, the Journal of Brazilian Chemical Society, which is a very important and big journal. Also, we edit a lot of books in different editions that we have. So there are books that have like over 10 editions already because a lot of people buy these books. We have an electronic newsletter, which is an important thing that we have. It's a weekly also. We have our annual meeting that I would like to invite you all to participate. It's not online, so you have to come to Brazil, and so it's a good opportunity to invite you to come to Brazil. Next year, it will be in Campinas. It's a city in São Paulo. It will be from 8th to 11th of June. We usually reunite more than 2,000 people. It's all the abstracts we receive are in English. We have a lot of international speakers also confirmed. And it's a really nice event, so I really invite you to come to this event. Campinas is a nice city. It has an international airport, so it's easy to come for all parts of Latin America, so please come to our meeting. Also, we have many important actions here in Brazil, for example, in the graduate, undergraduate, and scientific levels. So we have important actions that I won't go into detail, but you can visit our website and see it a little bit more. But for example, we're also responsible for the official periodic table in Brazil, for enabling this table, of course. And we are responsible for a lot of important public making actions here in Brazil. For example, we in funding agency, and also we partner with a lot of scientific societies. But let's go to the results. So talking about tackling these toxic organophosphates, I would like to talk about today three parts of what we have been doing. So we have been trying to develop, as I mentioned before, catalysts. So I'm going to talk about nanocatalysts, what I call sustainable catalysts. And finally, I want to mention how we do the detection also of these toxic chemicals. And this graph here just shows a little bit of the general spectrum of what we have been doing. So we have been using different kinds of supports as catalysts and evaluating if they're efficient. So you can see we have carbon nanomaterials, metallic nanoparticles, we have the sustainable materials and renewable biopolymers that I'll be showing here today. And so we have been exploring different kind of platforms so we can use toward these toxic chemicals. And I hope you will see that during my talk, we will align with several principles of green chemistry. I'm sure that tomorrow you'll hear the excellent talk by John Warner about green chemistry. And I will not get specific to this, but I can tell you that we are aligned with several principles in here. So we want to prevent pollution. We have atom economy. We want less hazardous chemicals. We design safer chemicals, safer solvents. So we want to neutralize something. So we see catalysts, for example. We reduce derivatives because we don't want byproducts. We use renewable resources. We design energy efficiency, of course. So we are concerned actually with the green chemistry, and we think that green chemistry is actually a very powerful tool for this kind of thing. So we tackle something that's very toxic using principles that are aligned with green chemistry. So in the first part, I want to talk about nanocatalysts. So in this part, what we're interested is the nano design. So we are focused in nanomaterials, specifically carbon nanomaterials, for example, because we think there are very interesting support which we can benefit from synergism. So what we have been doing in general, we have been obtaining over 30 nanocatalysts derived from different kinds of carbon nanomaterials. Usually our strategy is focused on functionalizing, for example, putting different groups on this material via, for example, the acid side, the carboxylic acid groups, or for example, the epoxy groups. So we have this route where we functionalize via the carboxylic acid groups, or this route where we functionalize via the epoxide. And why do we do this? Actually, we want to explore this kind of functionalities because, first of all, we know they're located in different places of our sheet. So one is on the basal plane, other on the borders, and we want to understand if this, for example, can affect the catalysis. If we could correlate the efficiencies that we have for catalysis with the strategy that we do for functionalization. And for this purpose, we not only change the strategy of functionalization, the synthesis, but also we can vary the degree of oxidation of our materials. So we can have more or less oxygenated groups, which are the sites that we functionalize. We can do the mono functionalization with one group, or also bifunctionalization. We can put two different groups there, try to mimic enzymes. We can use different kind of precursors, for example, not only graphene oxide, which I showed here, but also, for example, carbon nanotubes. And we can vary all kinds of groups that we can put there. So I showed you here some of them. So we have thiol groups, amine groups, imidazo groups. We can combine, we have hydroxamic acid groups. We can combine these groups, for example, with metallic nanoparticles, which have an interesting application that we'll show. And also we can combine two different groups on the same material. And we can obtain this material as powder, for example, or thin film. So this is one of the great advantages of using this carbon nanomaterials because we have an easy way to handle. So we can recycle them easily by filtering off, by just washing it off. And in the case of thin film, we have this example. So we have the thin film deposit on this glass. We can put it inside with this is a toxic chemical that we have, and it reacts with the thin film, which is deposited here. And the thin film is well adhered. It will not go to the solution. And after we have this yellowish color that says to us that the reaction has finished. Or we have this one. We have the nanocatalysts that we obtain from carbon nanomaterials, which are magnetic. So it's very easy to separate. So as I mentioned, one of the good ideas of using this carbon nanomaterials is the handling of these materials. So what's interesting about it is actually, so how good are these materials? When we talk about the lifetime here, we can see here that, for example, reaction, if we use this organophosphates here, reaction that just in water would take 15 days, we can reduce this to an hour and even less using our material. So this means it really is a good catalyst. If we use this other real-life pesticide, which is the Paraxone, the reaction in water is estimated in over millions of years. That means it won't happen. It will stay toxic for millions of years. And we can reduce this to a couple of days and even less than this more recently. So this means that these materials really have potential for neutralizing these chemicals. And also we can recycle this material. So we have been testing this for at least 3 cycles. In some cases, we tested it for even 10 cycles. So we can use the same material several times. So you can imagine that we can use the same catalyst deposited in a film to eliminate a stockpile and reuse it in different stockpiles, for example. And when we wanted to understand better the roots of functionalization, for example, we can see here this graph shows all the materials that have been synthesized, and this is the rate constant. So the faster this is, the higher this is, the faster it is, and the better it is. And we wanted to correlate. So is it better to functionalize via one group or the other one? And what we see actually is every time that we functionalize via the epoxide, for example, you can see here or here, it's always better. So this shows us that actually where we functionalize really affects our reaction. And it's also important to say that the bare molecules or support don't have a significant activity compared to what we show here. And we wanted to understand, so how can the support improve this reaction? What causes this kind of synergism? And one of our proposals is based on enzymatic mechanism, where we propose that, for example, if we have here would be our material which is functionalized, and this is the organophosphates. So this is, you have the group that we functionalize, and this is a neighboring group which is present already on a support, which is a carboxylate groups. Actually, it's a carboxylic acid groups in its anionic form. So you can see that what we propose that happens is this neighboring group can improve the catalysis of the group that we anchored by this hydrogen bond. So this hydrogen bond can really shift and switch the reactivity of a reaction. So this group is much better reacting towards a phosphorus, towards our toxic organophosphates, when we have this group nearby. And we have proved this by, for example, blocking this group nearby. And so this is one proposal that shows how the support really matters and affects our final outcome of the catalysis. And in the case of nanocomposites, that is, when we combine with metallic nanoparticles, we have another interesting thing. We have what we call the total neutralization, because we can use the materials that we functionalize and put metallic nanoparticles, for example, and first we can degrade, neutralize the organophosphates, which is very toxic, towards its product, which is a nitrophenol. It's less toxic, but it still has some toxicity. And in the same media, what we do is we put borohydrate and we can reduce this nitrophenol to nitroamine. So this is a final product which is less toxic. So we have two consecutive reactions which we can catalyze and lead to the total neutralization of what we had previously was really toxic. Another interesting thing is that we can use this nanocomposites also as sensors, for example, for SARS or electrochemical sensors to detect this kind of organophosphate. So I'm not going to bring these results here, but just to show that this kind of catalysts have potential not only for catalysis, but also for the detection. Well, going to the second part about the sustainable catalyst. So in this part, we're concerned with the materials that we get from biopolymers. So this sustainable support that we call the biopolymers, we call them biopolymers because they're biocompatible. So we have been using different kind of precursors. So we have, for example, carboxy methylcellulose. We have nanocellulose, which are considered cheap materials that we can use. We have been using some wastes also, for example, rice husk, which is an agricultural waste. We have been using gum arabic, which can be commercial or is also an industrial waste. We have shrimp shell, which is a fishery waste. And also we have some other renewable resources that we can use. For example, arginate, we can use cashew tree gum from Brazil. And also we can use a gum from a tree from the Amazon, which is called buchichão. So we have been getting all of this materials and functionalizing them in the same way that I showed before, very similar to that. Focusing especially on three different groups: hydroxamate, imidazole, and amidoxine, because these are one of the best groups that we found. And we functionalize these materials, and we obtain over 25 catalysts derived from these materials. And we can obtain these catalysts as homogeneous, for example, here, or heterogeneous materials. Okay. But anyway, in both cases, either homogeneous or heterogeneous, we can also recycle these materials for at least 5 cycles in this case. So we can use the same material several times in several different cycles. And afterwards, we have been confirming, for example, that functionality was maintained. Here you have a video just showing the reaction with the rice husk, for example, that we can use in the same medium to neutralize these organophosphates. But I would just like to show you here this graph that shows a general idea of all the materials that we functionalize. So here we have the rate constant, and here we have the biocatalyst that we obtained. So here we have the area where we have the rice husk and shrimp shell, so the waste materials. Here we have the gums, and here we have the cellulose and alginate, for example. So we have a broad spectrum of activity. All of them are very reactive, and we can't really say which is the best. Oh, you can say maybe this is the best one. But when you compare, for example, with this one, which is a waste, maybe this is a best option because we're reusing like rice husk, which is a waste already. Anyway, all of these materials show to be very promising for this kind of purpose, for neutralizing these toxic agents. And what we saw also is that when we use these polymers, these biopolymers, it's interesting because they have a very high selectivity. So the polymer, it shifts the selectivity towards having less byproducts. Because usually, for example, if you have this organophosphates, and here you would have the molecule that reacts, usually you can have this kind of two side reactions occurring, which obviously leads to byproducts that's not of our interest. And we see that when we use the polymer, when we use this group anchored on a polymer, we don't have one reaction. We just have one specific occurring, which is the most desired one because it leads to less toxic products. So this kind of selectivity is very important when we want to neutralize these organophosphates. On the other side, we also have an interesting aspect that when we functionalize the material, the rice husk, for example, with this group here, which is amidoxine, we have this property called scavenging. So that means that it can scavenge the organophosphate. So we can remove that from the medium. So that it could be very interesting. So not only we can catalyze the material, but we can remove it from the medium, concentrate in a more safe place, and then eliminate that. So for example, we can remove it and leave it to another safer place, and then we can remove that toxic chemical, for example. So here I can show you when we have this material that we functionalize with our organophosphates, we can have it in water, it acts as a catalyst. But if we change the solvent, so this property of scavenging is modulated by the solvent. So if we use, for example, acetone, we can scavenge this material. So it stays linked to here, and then we can remove this because it would be a solid material, and then take it to another safer place, another safer, you can see bottle or something like that, that we can then remove the scavenged material and then detoxify in a more concentrated way. Another interesting idea that we had with these biopolymers is that we can develop neutralizing gels. So the materials that we functionalize through carboxymethylcellulose, specifically, for example, with hydroxyamic acids or imidazole, we can get this kind of gels. And this is very interesting because this means that maybe this gel could be something to prevent intoxication, skin intoxication, because that's one of the greatest reason of intoxication that we have is in the field when applying this agrochemicals, for example. So here we tested this. So for example, here we have the gel without application of any agrochemical. And here at the end, we applied agrochemical, and you can see that the gel is yellowish. So this means that the gel neutralized the agrochemical. So he was in contact with the agrochemical and was able to eliminate the toxicity of the agrochemical and avoid that it comes to our skin. So I have a video here that I can show you that. Sorry, let me just show you again. So you can see here, we have a transparent gel, we apply the agrochemical, and then we get this yellowish color showing that the gel can neutralize this agrochemical and avoid intoxication. So you can see this representation here. So this can be used not only for agrochemicals, for example, but maybe in some kind of for chemical security reasons. So we have some kind of chemical emergency that could happen in some kind of place which can use chemical weapons. This can be a way to protect yourself. This is in gel that we made. And finally, the last part I want to bring to you is talk about detection. So we saw that using catalysts, developing this kind of materials are very promising, but we can also benefit from this catalyst and develop detection methods. One of them is actually a very simple one. We just developed this kind of what we call the homemade detector, which is colorimeter that we use using lead. And you can take this to the field, for example. And you can use this, for example, and study the reaction that we used, for example, with our catalyst and some of the agrochemicals. And we can detect the product which is formed using the system, which is very simple. And by this way, you can avoid, first of all, using big equipment or taking this to the lab. So you can do this in the field. And you can detect the presence, for example, in 5 minutes or 10 minutes of these chemicals. So this is actually very interesting, and it has a lot of promising outcomes, because we want to be able to go to the field and in the field see if we have some kind of problem or some kind of misuse of agrochemicals. Because in Brazil, usually we go to the field, we collect the food, we take it to the lab, and then some days, maybe a month after, you get the analysis. Sometimes you have a false positive, sometimes you have positive or negative. In this case, this could be like the first the first part, you can go to the field and do like a triage to see if what are really contaminated and just take to the lab what seems to be contaminated. Another idea that we had linked to that is we wanted to develop, this has nothing to do with catalysis, but this has to do with detection. So we maybe you have heard about glyphosate. This is a really big problem worldwide. It's one of the largest agrochemical that's being used still. And it has a lot of problems. It's been used in large amounts. And we wanted to develop a simple method for us to detect it. Because if you talk about degrading this, it's not so easy to do that. And it's not because it's not of great interest, but nowadays it's of great interest to detect the presence, because actually it's because it's such a simple molecule and small molecule, it's really hard to detect. So many of the analysis that we have for like a list of agrochemicals, they cover like 20 agrochemicals, and glyphosate sometimes is not there because it's very hard to detect. So we developed this simple method, which is called a coloring method, which we functionalize actually the glyphosate with something which is stable, and then we detect its color. So initially we have something that's transparent, and after we have something that's yellowish. So we can detect this very fast in 10 minutes, and this is in solution, but we can take this, for example, and into paper. So we can do a paper sensor using the same method. So this is a control one, and this is the one which I have glyphosate. Or you can use a glass sensor using the same reaction that we have been seeing here. Well, you can see here in this video, which we have a control sample, and here the contaminated one. So you can see here that the contaminated one starts to turn yellow. So you can see that by the amount of the material of the glyphosate, we can have a darker color, more yellowish or less yellowish, and we can correlate this with the concentration, for example, here. So we can have a correlation with the concentration. So this could be a nice way to detect and follow the presence of these toxic chemicals. And we evaluate also the effect of incipients or interference of incipients, because when we look at real-life agrochemicals containing glyphosates, we have a lot of incipients. The previous studies I've just showed you, we used pure glyphosate. But when we're going to apply this in the field, usually we have at least 50 to 80% incipients. So we wanted to understand if maybe this could affect or interfere in our method. And we tested with several different commercial names, which you have here, just getting the material directly without any purification. And we were able also to confirm the same method to detect this, and there was no interference of the incipient. Another interesting result that's very recent is that we also combined glyphosate with other agrochemicals to see if there were some kind of interference of our method, if there could be, for example, false positive. So instead of reacting with the glyphosate, it could react with another agrochemical which is present, which is usually applied together with glyphosate. And we have tested for 3 or 4, and we have been seeing very promising results, which in most cases, in all cases that we tested for now, at least for 4 agrochemicals, which we know in Brazil is applied together with glyphosate, they don't have any kind of interference. So we can apply them together. And now we're testing with some other molecules, which is found together with glyphosate, for example, AMPA. And finally, so as a summary overall, I would like to highlight that regarding the greening up, I hope I have convinced you that we have been following several principles of green chemistry. We develop catalysts, so we are seeking faster processes. We are seeking recycling processes. We're trying to avoid byproducts. We're trying to neutralize and detect very toxic agents, and through methods which are more sustainable, using more friendly, sustainable, environmentally friendly solvents, for example, using renewable precursors, trying to use supports which can benefit from synergism, so they have a higher efficiency, for example, for our purpose. And we have been using them to tackle these toxic organic chemicals. So this is just a general idea of all the materials that we have been functionalizing. And I would just like to mention that we have been also studying molecules which are not functionalized. So that's what I call molecular catalysis. And this is also very promising. We can also have a lot of molecular catalysis, which can be efficient and selective also for this kind of reaction. And I have shown you also that the strategy we functionalize, that is not only where we functionalize, but the precursor that we're using can really boost up or switch the catalysis. So for example, I showed you that the neighboring groups that we have on the supports, for example, carboxylate groups, it can really boost up the catalysis. I'm calling the same because I think it really, if we remove this group, we have a lower catalysis. And if we put this group there, we have a much more efficient catalysis. So it's much faster. So this means that the synergism really happens, and the precursors matters. It's just not, it's not just a support that doesn't react or doesn't participate in the reaction. The precursor really matters. And also we can see that depending on the material and how we functionalize, we can have multiple catalysis. So for example, I showed you the total neutralization of organophosphates in the case where we were able also to reduce nitrophenol together with the neutralization of organophosphates. So this is a general idea of how we have been tackling toxic organophosphates using neutralization and detection. And finally, I would like to show you just some nice pictures from Brazil, seeking to convince you all to come to Brazil next year for our annual meeting or maybe some other kind of event. I'm also always open for collaboration. These are my contacts, and I thank you again, and thank the organizing committee of the event for this really, really nice invitation. Thank you.
Thank you, Elisa, for your talk. Very inspiring. I actually love to see lots of, I don't know, how to say, the molecules, and trying to put everything together. And it's somebody that might not know a little bit might think that we're just taking a little bit of everything to obtain a result, but it actually love how to see how chemistry can be applied and also improve our way of living, something that most of the time it's very forgetful for people. People, if you do have questions or comments, you can do it right now, whether you want to open up your mics or if you want to comment something on the chat. Also, if you don't speak any English and you want to do the questions in Spanish, there's no problem. I'll translate them. I'll start by myself. I would like to know about the gel. I will the one that detected the organophosphates. If you're thinking to patent it, or maybe to also have a collaboration with the industry to mass production, hopefully.
Yeah, that's a great question. Actually, this are very recent results, and we are in the process of publishing this and also submitting the patent, because I personally don't have any experience with this interaction with the industry, but I'm very open to that. So I already have 3 patents that we have deposit before regarding this kind of procedures that could be interesting for the industry, for detection, for neutralization. And now we are hoping that we can develop this kind of gels, maybe sprays. The next step would be sprays, for example. So we can have like a neutralizing spray that you can put on the body. Also, you can have something on your clothes, for example, that you use on your mask that can detect and also protect yourself.
Yeah. I mean, that's something that we talked yesterday with Javier. He said that we needed to make contacts with the industry and everything, which is something that right now we don't have it. But now the times are changing, so you need to move to that part, and maybe also there's an opening from the industry to see these new opportunities to use the more natural stuff, like the products that you have there, and maybe you use it as waste. Maybe you have it as waste to valorize them and make chemistry with them. But yeah, baby steps right now.
Yeah.
Yeah. Anyone would like to ask something or to say something? Okay. Max David Corona said, very nice talk. I have a question. How to complicate how complicated is functionalized biomaterials and study the mechanism?
It's a very good question. So it's, I mean, the hardest part, I mean, there are many hard parts, I think, of this, but when we're trying to functionalize these biomaterials, the first thing that we need to know is they can be their structure can vary a lot if you get from different resources. So you first of all have to characterize the material very precisely so you know what we're dealing with. And afterwards, you can do the functionalization. Because if not, if you functionalize, for example, with one batch, and then 1 year after you functionalize with another batch, they're not even comparable. You don't know if it's like an effect. Because afterwards, you want to really study, for example, the mechanism. So, for example, I want to understand, as I mentioned before, the effect of neighboring groups. So I think that possibly the carboxylic acid groups are important. What do? I block them. So I do a specific functionalization to block these carboxylic acid groups. But I need to be sure that I'm comparing the same materials. So it's very common, for example, for biomaterials, for example, these gums, these wastes, to have very different structures. So in one case, you can have like 40% of acids, in the other case, you have 20%, you can have more proteins, less protein. So all of this can really affect. So my concern, first of all, is always to collaborate with someone that can do this first part, because I'm not very experienced, to guarantee that you can, first of all, extract the gum, for example, from the cashew tree, and you have this gum, which is well characterized, and we know it's specific. So we're going to do all of our study with this batch, so we know how much we have there, how many acids. And then we have to find a functionalization strategy, which can be selective for what we want. So we want to put a group there, we have to be sure that it's there. So this took a while because we based ourselves on the literature, but also sometimes it didn't work. So we had to increase the concentration, increase the pH. So it was like, it has been going on for some years for us to optimize the conditions for the synthesis. And after, when we want to propose a mechanism, that's very difficult because you're talking about a very complex molecule. So, I mean, the organophosphate is very simple, but the biopolymers, it's enormous. So you can't really see the mechanism, for example, very precisely by NMR. You can see that's why we talk about molecular catalysis. We study these simple reactions because we can follow this by NMR, we can follow this by computational results, studies, we can follow this by mass spectroscopy. But when we talk about biopolymers, it's very big, it's very difficult to see this. But we have some strategies. One of them, in some cases, depending on the degree of functionalization, we can follow them by NMR. We have been seeing this. In other cases, we have been, for example, we vary the structure of our organophosphates to correlate to the mechanism. So, for example, if you change the reactivity of what's reacting, maybe indicate on the mechanism. We try to, for example, block the groups. We try to use different kinds of biomaterials, which have more or less oxygenated groups. And then we try to correlate this with activity. So it's like a correlation that we do with the structure, maybe structural factors, with the outcome in the end. So it's not very straightforward. I don't know if I answered your question, but it's like a one student has to study one principle, the other student has to study other principle, and then we evolve from that. So to get, for example, to the gel, somebody had to do all the functionalization before and optimize the steps.
Thank you for the answer. I think the main summary is team effort. But yeah.
Thank you.
Walter.
Well, can you hear me?
Yes.
Yes,
Okay.
we can.
The video is here.
Yeah.
Elisa, thank you very much for the presentation. It was amazing work. Jesus Christ. And I would like to, I saw your emphasis on detection and neutralization, but I work with some microplastics, some plastic sources, still using organophosphates. And I was just checking the Plasticam database, just released this year, and we have a few organophosphates in use, still in use. What's your, is it okay? Is it okay? Is there some work on looking for safer alternatives? Can you give your idea about that, please?
Thank you, Walter, for this question. Yeah, that's a really big concern. When I have a little bit more time and we talk about the importance of organophosphates, we always say that they're present in chemicals, chemical weapons, and also the plastics. They are being widely used also. It's another class. I mean, it's organophosphates. They're less toxic, so they can't really be used as a chemical weapon, actually. I mean, everything can be used as a chemical weapon depending on concentration. But they are, of course, there's a lot of concern. So there are a lot of people that are trying to find substitutes for these organophosphates. Not only, for example, to substitute the use in plastics, for example, but also in the synthesis and to have like a more reliable standards. So sometimes we have to be able to synthesize the materials. So they're trying to find, first of all, safer ways to synthesize these materials and try to find molecules that can replace them. Not only, for example, for the application that you mentioned, but also, for example, for our chemicals. So there are some people that are trying to, they get like organophosphate and it functionalizes with like this big alloic chain that's more sustainable and try to see if it still maintains the property of avoiding of acting as a chemical, but is much less toxic. So they're trying to correlate different structures of these organophosphates by changing the substituents and correlating the maybe a less toxicity, easier way to eliminate them with the structure. So there are some, I'm not really focused on this, but there are people which are concerned with that. And I think it's a really big issue.
Okay. Thank you very much.
Thank you.
Any other questions, people? Well, while we wait, I would like to ask about the importance, something that actually piqued my attention. It's that the Sociedade Brasileira de Química, it's very focused on the young research, which is something that still we have to deal with a lot of other chemical organizations. For example, in my country, there's no there is no people, or there seem to be not an effort dedicated in this. And I would like to know, what are you doing as a society to encourage young researchers to come to organize and to also look for other opportunities for
So you're talking about young researchers already with in an institution, like research already, right? Not young like undergraduate.
No, not undergraduate. Okay. But if you do have something for undergraduates, I think it will be very interesting to know.
Okay, so yeah, so our society, since we are a little bit old, I mean, we're completing 48 years, we have been engaged in several activities, and more recently, we found the need to talk to those young researchers. So now we're talking about the young teachers that just got a position in the university, and we have like this society that had a lot of, I mean, old people. I hope they're not here, so they'll be very mad at me. Walter, you're not considered old, okay? You're young. But we needed to engage with them and talk to them, and we wanted to attract them. So first of all, we created a group called Young Researchers of SBQ, and they are elected by the society. So they're our young members, they vote on this and they decide who will be representing them on this board. So this is a board of young researchers. So what do? They talk to the directory board to give new proposals of what to do. They have a lot of different actions. They're really independent. They have like a podcast that they do. They have a lot of events that they do. And also we always give them space in our annual meeting, because maybe our highlight of our society is our annual meeting. So they have a space that they can have their events, come to reunite these young researchers to talk about. So we always putting them together to talk. We give them space in our event to talk, and they're always giving us demands of what they want to do. They want to present something somewhere. They want to participate. So they're participating in the decisions that we're making. So, for example, when we invite now new speakers, we are also not only concerned with gender parity, regional we also are concerned with the regional thing, because Brazil is very big and we don't usually have a lot of people from São Paulo. We want to be able to get people from other places of Brazil, but we are also concerned in having young researchers, because when a young researcher sees another one talking there, he said, oh, I can be that also. So, I mean, we have been improving this, and also putting them also in all of the committees that we have. So we have a lot of committees that we participate, and also we are asked as a society to indicate names. So, for example, in funding agencies and boards are going to be judging, for example, scholarships. So we are putting all of these people together and trying to give them opportunities also. And regarding the undergraduates, well, we have a lot of programs. For example, we have like a unified exam here in Brazil for undergraduates which do this exam so they can go into a graduate course for a PhD or master course. So we have like SPQ is organizing this unified exam. We have a lot of graduate courses here that we also are supporting. And in our annual meeting, we always have what we call SPQ in school, where we receive students from public schools, and we have like a big place where we have a lot of tables where we show experiments. And so we have our community showing people, and it's supposed to be students from school. So it's like high school, middle school students, which go there, and usually from public schools. And they get to have like during 4 days to experience chemistry. And usually we see like more than 2,000 students for this kind of purpose. And also our journals, because since we are editing, we have our editor, our publisher, which we have 4 magazines. Among them, we have one that's specific for school. It's called SPQ in School. So we have, it's engaged actually in showing experiments and highlighting what was successful in this kind of way.
Which is good to know that you're considering the young researchers and also giving a place for undergrads and the teaching community in high schools and middle schools. That's why most of us are already here. So Pedro said, thank you very much. Very interesting session. And also Walter had to leave, and he said, amazing work, Elisa. Proud of my fellow and dear Brazilian colleague. And without further ado, if none of you have any other questions, I will finish this session. Thank you so much, Elisa, for having a time with us to talk about your research, to talk about what you're doing in the society, in the chemical society, and to inspire us a little bit more. So thank you for your time. Thank you for everything. And we'll hopefully see you in another time.
Thank you very much for this opportunity. I was very happy to be here. And thank you all for the questions. And again, for this opportunity to be here.
Okay. Thank you very much to our attendees also for accompanying us. And we'll stop the recording right now, and you're free to go. You can also see this talk on YouTube, where we're going to upload it in the next few days. So thank you very much, and have a good day.
Thank you. Bye-bye.
Thank you. Bye, Lisa. Thank you.